All right, so let's look at how to draw shear force and bending moment diagrams. We'll start with the very simplest of them, which is your point loads. We'll start with point loads. So take that, please. Draw the shear force and bending moment diagram for the beam below. Draw the shear force and bending moment diagram for the beam below. Draw the shear force and bending moment diagram for the beam below. For the beam below. All right. Example number 1, draw the shear force and bending moment diagram for the beam below. You have this. Question 1, what kind of beam is this? What's a point load? What kind of beam is this? Simply or what there? Freely supported beam. Look at this. The supports are at the extreme. That makes it a simply or freely supported beam. That's one. Number 2, how many kinds of support do you have here? 2, which and which? Fixed and roller. When you check your exam questions, in most cases, you will see a fixed and roller or a roller and roller. In most cases, you see a fixed and roller or roller and roller. But majorly, at your level, you'll be seeing fixed and roller, fixed and roller. Do you know why? You know why? Simple. The reason why you be seeing fixed and just be observing your questions. The one last year, they just gave you the stuff straight. But if you check it, you all be seeing fixed and roller. Why do most beams come with fixed and roller support? Simple. Because of something called what there? Thermal expansion. That's it. So the concept is this. What fixed beam does is that it holds the beam to a particular place. And if you have a case where you put 2 fixed beam, what fixed support does is that fixed support holds the beam firm at a particular point. In a case where you apply 2 fixed support to a beam, what happens when the beam wants to expand? Let's say because of the sun, right? No, sun hits on it and it wants to expand. Thermal expansion. If sun hits on this thing here and this one wants to expand, and you're having 2 fixed support, it will crack. Because literally the stuff wants to expand, it wants to set free, but then it's being held tight. What happens to it now? It will do what there? It will crack. That's the concept. So the idea of putting the roller and the fixed is such that if this man wants to expand because of thermal expansion or because of sun, it has what there? That space. Due to the roller, it will expand a bit. And then what happens when it cools down? It will do what there? Contract. So it's also what there? Move freely. So this roller concept is to allow the free movement of the beam due to thermal expansion and what there? Thermal contraction. Thermal contraction. Okay. Contraction. Okay. So that's the concept anyways. That's the concept. Now let's move. When you're giving your shear force, when you're given a beam and asked to draw your shear force and bending moment diagram, what's your first step? Please, your first step is to draw your free body diagram. So please, step 1, draw a, I'm calling it FBD. Okay, let me just write there. Free body diagram. Free body diagram is called FBD. That's it. Free body diagram is called an FBD. What's a free body diagram? A free body diagram is simply what there? A diagram that shows all the forces acting what there on a particular system at a particular time. That's a free body diagram. A diagram that shows all the forces acting on a particular system at a particular time. That's called a free body diagram. But then leave the English alone. When it comes to drawing free body diagram for solid mechanics or for strength of materials, your concept is simple. Take off the support system and put vertically upward forces. That's all. To draw your free body diagram, it's as simple as take off the support system and impute vertically upward forces. If I look at this, I have support systems at two ends. This end here, call it A, this end here, B. Now, by the way, in your exam, they'll give you points A, B, C, and D. It still works. So what does that mean? It means that solution, you will redraw this. So draw free body diagram. I said your free body diagram is very easy. Take off the support system and put in vertically upward forces. This one here and this one here. That's all. That's all. Take off support system, put in vertically upward forces. That's all. The next thing to do is to call those forces reactions. Reactions. Now, for the first one here, the alphabet here is A. So the reaction here becomes arrow A. The reaction at A. The reaction here becomes B. So I have arrow B, reaction at B. In essence, if I had this diagram as A, B, C, D, I'll have arrow A and what there? Arrow D. Please. Arrow A and arrow D. But since it's A and B, we have arrow A and arrow B. First two steps, check. Number one, take off support systems, call them vertically upward forces. That's simply your free body diagram. Anyways, that's it. All right, so what next? Number two, this beam here, is it statically determinate or statically indeterminate? Statically determinate beam. It means I have to bring in the conditions of static equilibrium. Bring in the conditions of static equilibrium. I'll try not to deviate, just to stay in place. I give you three conditions for static equilibrium. Number one, summation of vertical forces equal to 0. Number two, summation of horizontal forces equal to 0. Number three, moment at any point equal to 0. Look at this stuff, please. Do we have any horizontal force here? Huh? Is any force going horizontally? It's just what there? Vertical forces. In total, how many vertical forces do you have here? In total, how many vertical forces? In total, how many? 4. 1, 2, this is still the same thing. 3 and 4. In total, I have 4 vertical forces. Now, here, I will say summation. So I'm now bringing in the conditions of static equilibrium. So summation of vertical forces equal to 0. So I have sigma summation. Vertical is Fy, right? Y is for vertical axis. Fy equal to 0. Now, in this stuff here, look up, please. In this stuff here, I'll put this. I'll put upwards. I'll put plus. What does that mean? Going up is what there? Positive. So if it's not going up, it becomes what there? So look up, please. Look up. Look up. Here's how to do this. We have 4 vertical forces. All the ones going upwards should be positive. All the ones coming downwards should be negative. This man is going what there? So it becomes what? RA. That's all. This man is coming what there? So it becomes what? Minus. What's the value? 20. This man is coming what there? Downward. So it becomes what there? Negative. Minus 30. This man is going what there? Up. So it becomes what there? Plus RB. It's equal to what there? Summation of vertical forces equal to 0. It's going up, positive. It's coming down, negative. Some authors do the opposite. Some authors will say if it's coming down, positive. If it's going up, negative. You still have the same answer. Right, so you can try that way. So depending on your author, some author will say if it's going up, it should be negative. If it's coming down, it should be positive. Try it that way. We'll have the same thing. We'll have the same thing. So, but for me, I'm going this way, please. All right. Let's take it like terms. This becomes RA minus 20 minus 30 gives you what there? Minus 50 plus RB equal to 0. Obviously, move this man here, over here. That gives you what there? RA plus RB minus 50 comes, it becomes what there? Plus 50. What's your unit? Kilonewton. Call this equation 1. Please follow me up. Call that equation 1. So that's how you get equation 1. RA plus RB equal to 50 kilonewton. We've taken the first condition of static equilibrium. Summation of vertical forces equal to 0. It has given us an equation. The second condition of static equilibrium says that summation of horizontal forces gives us 0. There is no horizontal force, so we'll skip it. We'll go to what there? The third one. What's the third condition? Moment about any point gives you what there? 0. All right. So here's what we do. We'll take moment about any of the points. We'll take moment either at A or at B. Any one you choose to use would give you the same answer at the end. That's the beauty of this stuff. So I said it's not a one process thing. You can be doing it left, left, left. You can be doing let up be positive, let down be negative. I'll be doing let up be negative, let down be positive. I'll still have the same answer as you. You can be doing take moment about A. Me, I'll be doing take moment about B. At the end, we'll have exactly the same answer. How do we take moments? So at this point here, you decide the point to take moments about either at A or at B. Which do we take, A or B? Okay, so taking moment about B. So taking moment about point B. Now, here's the thing. I gave words, I gave symbolic representation. Words, symbolic representation. I will now say the sum, sigma, of moment M about point B, B is equal to 0. Please understand this. The sum, this one was the sum of Fy, force vertical. Vertical force is equal to 0. The sum of moment about B. I didn't write MB. This is megabyte. I wrote M subscript B. For those of you that will say you didn't see this, look at this. This is what I wrote. Next up, we'll consider direction. Please, when we do clockwise, we know that clockwise is this. Abi? Who doesn't understand this? Let me know, please. No, who doesn't understand this? Who doesn't know what this is? Looking at clockwise movement. So the hands of a clock turns this way. The hands of a clock turns this way. So we said, let clockwise be positive. So I'll now come here and I'll say, I'll say, let this be positive. So know what I mean by this. If it's clockwise, it's positive. If it's not clockwise, it becomes what there? Negative. Anti-clockwise is negative. Understand these things. All right. We are now taking movement about this point here, B, this point here. So all you're doing is that you're moving the forces from where they are to B. That's all. If it goes clockwise, positive. If it goes anti-clockwise, anti-clockwise, it's what there? Negative. So let's start with the first force here. This is point B. We'll start with this one here. This one is going up. So I'll trace it up to this point. So it's just simply up, goes like this onto B. So here's my direction. Look at this very well. This movement like this. Clockwise or anti-clockwise? Clockwise. It becomes what there? Positive. So I have positive RA. Movement is simply the product of what there? Force and perpendicular distance. It becomes force times distance. From what you have there, what's the distance from RA to B? What's the total distance from RA to B? From here 2 meters, 2 plus 3, 5 meters, 5 plus 2, 7 meters. RA times 7. We are done with RA. This man goes off. Let's go with 20. So I said 3 seats to that point. This man is coming down, so I'm chasing this down this way. My movement is like this. What you have here, clockwise or anti-clockwise, is anti-clockwise. So it becomes what there? Negative. It becomes minus 20. Distance from 20 to RB, what do you have? 5. From here to this point becomes 3 plus 2. That's 5. Next up, this man here, going down to this way. Look at this movement here. Clockwise or anti-clockwise? It's anti-clockwise. So it becomes what there? Negative. Minus the value there, 30. Distance from here to here, 2. Do we include RB? Do we include RB? If you include RB, I'm thinking about this point here. If you want to put RB, what's the distance of RB? So when you're solving this, in most cases, they don't include RB. Know why? In essence, if I'm taking moment about RB, if I'm taking moment about B, I don't have to include RB because RB is exactly at B. So if you take the moment, it becomes RB time. What's distance here? No distance. It's at that point. So it becomes what there? 0. In essence, if I were to take moment about A, that's here, will I include RA? No. Why? RA is at that point. So distance becomes what there? 0. So I'll not include RB. That's equal to 0. Please note, you don't include the reaction at that point. That's it. Why? Because the reaction will give you what there is 0 distance. So anything times 0 is 0. It becomes useless. So leave it out. All right, let's get this done very fast. I have 7 RA minus 100 minus 60 equals 0. So I have this. 100 minus 20 times 5, 100, 30 times 2, 60. I have 7 RA, this and this, minus 160 equal to 0. Move this man over here. I have 7 RA is equal to what there? 160. So minus 160 comes, it becomes what there? Plus 160. Let's get RA. To get RA, I will divide here by 7. Divide here by 7. This cancels this. So I'll have that RA, sorry, 32.9. Did you approximate well? If you are approximating, my advice would be approximate to 2 decimal places. What do you have? 2 decimal. 86. Please use 2 decimal, please. When you come to year 2 second semester, you do something called numerical analysis and error analysis. You will know why we are using 2 decimal places. The more the number of decimal places, the more accurate your result becomes. This statement is verifiable in your second semester year 2 maths. One will do numerical analysis and error analysis. What I'm saying is this. If you use the value of gravity, G, for instance, as 9.81, it will give you a more accurate result than if you use G as what there? 9.8 or even 10. The more the number of decimal places used, the more accurate your result is. So I'm using 2 decimal places. All right, I've gotten RA. I'll put it into 1 to get RB. So put RA into equation 1. Put RA into equation 1. What do I have there? I have that RA, which is 22.86. That's RA plus RB is equal to 50. I'll simply move this man over here. I'll now have that RB is equal to 50 minus 22.86. I'll now have that RB is equal to, please give me value. Please hang on, I'm coming. Yes, you have what there? 27.14 kilonewton. Look at something. Look at something. Leave beams for now. Leave beams alone for now. Let's look at common sense something. Common sense. Look at common sense. I have two men, man A smiling, man B perhaps not smiling. And this is his leg, oh please. There two are holding a plank upwards like this. The plank, I distributed the plank evenly like this. So 2, 3, 2. Literally, these stuffs are evenly spaced. If I place a load here of 50 Newton and place a load here of 50 Newton, which of them will feel the greater impact of the load, A or B? I place them at equal distance. 2 to this side, 2 to this side, 3 at the center. And I place the same load on each of them, 50 and 50. Man A and man B, who will feel the greater effect of the force, A or B? Huh? It will be the same, right? Yes. It's equal load at what there? Literally the same space. They will feel the same effect. If I come here and place a greater load here, let's call this 80. Between man A and B, who will feel greater force? Huh? A. Why A? Because the greater load is what there? Close to A. Fine. This is 80. This is 150. Between 80 and between A and B, who will feel greater force? A or B? B. Why B? Because the greater load is close to what there? B. In my solving, if you give me this, I don't have to solve. Common sense will tell me that RB will be greater than what there? RA. Look at the value there. RB, RA. Where's RA? Look at this. RB, RA. Why? Because of what there? The greater load is what there? Closer to what there? RB. So even if I even start writing, I know the one that will be bigger. So by the time I look at this and I'm seeing that RA is bigger than RB, there's a problem somewhere. Just common sense. Just common sense. So if you give me a diagram to start solving, me looking at the diagram, I've already started anticipating my answer. I know what it will look like. It's not that difficult. All right, that's by the way. Let's proceed. So your first task is to draw free body diagram, which we've done. From that, get the value of the reactions, RA and RB, using the conditions of equilibrium, vertical forces, moment. You have that stuff. All right. Let me know. We took moment about B and we got this. Should we try taking moment about A and see what we get? Huh? Or let's try it. All right, just look up. What if I have taken moment about A? Let me say taking moment. Since this is not my major process, I'll just go straight. I'll say sum of moments about A should be equal to 0, and I'll call this what there? Clockwise. Let's now take moment about A, this point here. First things first, this man is coming here, this coming here, this going this way. So let's check this one, please. This is coming down this way. This motion here, clockwise or anti-clockwise? Hey, calm down, look at this. Now, you see why I said this thing is not a formula thing. Something that is anti-clockwise in one direction can be what there? Clockwise in another. Keep your mind open. That this man was anti-clockwise when we took against B does not mean it's always anti-clockwise. No. Keep your mind open. This is A. I am taking moment about A. I said just trace the force down to that point. This man is coming down to this point like this. Look at this. What you have here like this. Is it clockwise, anti-clockwise? Clockwise. Moment is force times distance. It becomes 20 times 2. A clockwise moment. 20 times 2. Okay? This man too is coming down. So down like this to this point. Down like this to this point. What you have here, clockwise or anti-clockwise? Clockwise. It becomes force. Clockwise makes it positive. So positive, the force here is 30. What's the distance? 5. Plus 30 times 5. Plus 30 times 5. Finally, RB. RB is going up like this way. Look at this, please. Clockwise or anti-clockwise? Anti-clockwise, going up like, look at this motion here, up like this. Up this way to A. That's anti-clockwise, becomes negative of RB. Distance from RB becomes what there? This is 2 plus 3, 5 plus 2, 7. So I have 7. I have stressed that you won't put RA, Abi. Why? Distance is 0. So it becomes what there? Equal to 0. 20 times 2, what do you have there? 40 plus 30 times 5, 150 minus 7 RB equal to 0. 40 plus 150, 190 minus 7 RB equal to 0. Move this man over here. 190 comes here. 7 RB. The negative becomes positive. Divide here by 7. Divide here by 7. What's RB? 27 point what? 1 point what there? Same answer. That's the thing about it. So don't just do any one. Your guy is do the other one. You still have the same answer. Don't stress. Just do your thing. Just make sure you're correct. You have the same answer. All right, so look up. Look up, please. So that's this was just by the way, just to show you how it's done. Now, when you're done with this, look up. When you're done with this, getting the value of the reactions, RA and RB, your next task is to get what is called the shear force calculation. Look up, please. Your next task is to get what's called the shear force calculation. Shear force calculation. All right. Shear force calculation. So look up. Look up. Please just listen to this and get how it works. Your first task in every shear force bending moment diagram is to get the value of the reactions, which we've done here. Your second task is to do a shear force calculation. Now listen, I won't want to waste your time. I'll go straight to the point. When you're doing shear force calculation, I'll be taking intervals at specific points on the beam. I'll be taking intervals at specific points on the beam. My advice to you is that take specific intervals at every point you have a point load. Please listen. Take specific intervals at every point you have a point load. In this beam here, I have a point load at 1, 2, 3, and 4. In essence, I will take at x equal to, please, at this point. Now, hang on. At this point, what's the value here? 2 meters. At this point, what's the value here? 0. 0, good. Because this is my starting point. My first thing there, at x equal to what there? That's all. So I will take at x equal to 0, at x equal to 2, at x equal to 5, 2 plus 3, at x equal to what there? 7. Why? That's the point I have out there, point loads. At x equal to RA, again, listen. At that point, the concept is simple. To do shear force calculation, you say the force there, is it going up or is it coming down? If it's going up, take it as what there? Positive. If it's coming down, take it as what there? Negative. At x equal to 0, this point here, please, do you have a point load there? Do you have a load there? Yes, now it's going up. In as much as, if you check, I give you point load as what there? Going what there? Up or what there? Down. This is a point load. What's the point load? What point load do you have there? So at x equal to 0, number 1, shear force is equal to RA. RA is positive. Why? It's going up. What's the value of RA? That's all. That's all. At, please, what will be my second interval? Where? At x equal to what? 2 meters. It will be 2 meters. Why is it 2 meters? I have a second point load here. Now, please listen. Please listen. At every point where you have a point load, you will take 2 conditions. They won't teach you like this in class. Just listen. That's why I said it will be looking like, what are you doing? What are you doing? But just listen. Right? When we solve second example, third example, you get it better. At every point where you have a point load, you add what there? 2 conditions. So at x equal to 2 meters, you add what there? 2 conditions. Condition 1 refers to all the forces before that point. Shear force calculation. For shear force calculation, I said for shear force calculation, you should take intervals at where you have point loads. I have a point load at 1, 2, 3, 4. Here's my first point. At this point, what's the value of x? X is 0. Y, starting point. At x equal to 0 here, do you have a point load there? Yes. What's your point load? RA. At this point, RA, is it going up or down? It's going up. We say when forces are going up, should it be positive or negative? So you now have positive RA, that's all. The next point is here. That's at x equal to what there? 2 meters, this one here. And I'm saying this, whenever you have a point load, put what there? 2 conditions. Condition 1 is usually shear force is equal to all the forces before that point. That's it. All the forces, you can add it there. Condition 1 is always all the forces before that point. That's all. All the forces before that point. So look up, please. Right and look up, right and look up, right and look up. All the forces before that point. Right and look up. Before, in quote, like this. Before this point, do you have any force here? How many? 1. What's the force there? RA. RA, is it going up or is it coming down? So before that point, I have RA. What's the value of RA? 22.86 kilonewton. Condition 2, shear force is equal to all the forces before that point plus the force at that point. See at this point here. Before this point, what do we have? Before this point, what do you have here? RA. It was going what there? Up. So before the point, that's what you have here. That's simply RA. Again, forces before that point plus the force at that point. At this point, do you have a force there? That's a point load. Going up or coming down? If it's coming down, should it be positive or negative? Negative. Becomes negative of the value. That becomes minus what there? 20. That's all. So RA minus 20. That's equal to RA is 22.86 minus 20. What's the value here? That's 2.86 kilonewton. That's all. All the forces before that point, condition 1, and by condition 2, all the forces before that point plus the force at that point. Please tell me, what will my next interval be at x equal to what? Huh? Not just 5 meters. If you put 5, I'll just put dollars for you, $5. Let's go to $5. At x equal to 5 meters, please, meters. At x equal to 5 meters, please, do you have a point load there? At x equal to 5 meters, do you have a point load there? Yes. So what do you bring in? Two conditions. At every point, you have a point load. Bring in what there? At x equal to 5 meters, that's here, right? 2 plus 3 is 5. At 5, do I have a point load? Yes. What will I bring in there? Two conditions. And I have two conditions. All right. Two condition. Condition 1. What's the idea behind condition 1? All the forces before that point. Where's my 5 meters? This is it. Before this point, do I have forces here? How many? 2. Which and which? RA and what there? 20. Which is going up? So it becomes what there? Positive. Which is coming down? So it becomes what there? Negative. So before that point, I have these two. RA going up, positive. 20 coming down, negative. Minus 20. And that's equal to RA is 22.86 minus 20. That's 2.86 kilonewton. That's all. Let's now do condition 2. All right. Condition 2. Condition 2. Let me see your group, please. Condition 2. The shear force is equal to. One second condition. All the forces before that point plus the force at that point. Please look up, please. At this, before that point, I have what there? This and this. That becomes RA. This coming down minus 20. Now, add the one at that point. At this point, what do you have there? 30. Going up or coming down? So it becomes what there? Negative. Negative. So it becomes what there? Minus 30. And that's equal to, that's 22.86 minus 20 minus 30. What do you have there, please? Please, point. What do you have? Minus 27.1114 kilonewton. Right. Okay, that's interesting. 14 kilonewton. All right. What's the last point? Huh? At x equal to what? At x equal to what there? 7 meters. Please, do we have a point load at 7? Yeah? Okay, so what do we bring in? Two conditions. Please don't forget two conditions first. Two conditions. Condition 1, shear force is equal to all the forces before that point. Where is my point? Here. What are the forces before here? Before here, I have 3 forces. 1, 2, and 3. This man is going up, becomes RA positive. This man is coming down, becomes negative 20. This man is coming down, becomes negative 30. So I have this. If I solve this, this is equal to RA is 22.86 minus 20 minus 30, and my value is about 27.14 in kilonewton. Yep, have this. Condition 2. Shear force is equal to all the forces before that point plus the force at that point. Before this point, I have RA, I have coming down minus 20, minus coming down 30. At this point, I have what there? RB. Going what there? Upward. So it becomes what there? Positive. Plus RB. Right, so that's it. Sorry? Okay, minus. Thank you. Thank you. Minus 27.14. Thank you. Minus, thank you, 0.14. All right, let's add this. This is equal to RA 22.86 minus 20 minus 30 plus, what's RB again? 27.14. Sum this, what do you have there? Listen and listen carefully. Shear force must always end with zero. Shear force must always end with zero. At this point, I am done calculating shear force because I'm done with the last one. Your very last value of shear force must be zero. Else, you're wrong. There are no two ways about it. Technically, if your shear force at that point is not equal to zero, what it implies in a real life concept is that this structure that we are keeping here will not hold. It will collapse, actually. So if shear force is equal to zero, that means this structure can actually work. That's it. So just side note, if your shear force is not giving you zero at the end, most likely you're wrong. But the real life implication means that the diagram, something is wrong with the diagram. That means the whole thing. If I set up this structure in a real sense, and I put a 20 Newton force, 20 kilonewton, and 30 kilonewton force, the structure do what there? It will collapse. It's not working. That's the thing there. But in exam case, we'll say you're wrong. In higher examples, it might not give you zero. It might give something like zero. Now we'll do higher when you sit there. To now give you at the end, your answer will now become 0.000012. That's the zero. Because you're using what there? Approximation. Or we can have something like minus 0.015. It's still what there? Zero. It's just due to what there? Approximation. But for now, always observe that your shear force will give you what there? Zero. Shear force. Check our first example. Our first example was not zero. Check. What would this shear force at x equal to 0? What was the first value? 20 what? It was RA. That was what there? 22.86. So here's the thing. Shear force must not start with 0. In some instances, it will start with 0. We'll look at it. But always note this. Shear force may or may not start with 0, but it must end with 0. That's it. Yes, sure. Let's say. They won't ask you. Don't worry. Don't ask you. Not in this USA exam. Don't stress. Don't ask you. Check your passage. Don't ask you. For what? You see in the diagram. Okay. You're saying why do you have 2 for these ones, but not this one here? Okay, listen. Good question. I said at every listen. Good question. Listen, please. Why do we have 2 conditions at every point load like this one here? Look at this. We took 2 conditions, 2 conditions, 2 conditions. There was no 2 condition here. Why? Simple. In the concept of 2 conditions, condition 1 is always what there? All the forces before that point. Condition 2, all the forces before that point plus the one at that point. If you take at this point here, condition 1, this is the start of the beam. All the forces before that point. Please, before this point, what do you have here? So no distress. That's why. So you ignore it here when it's at the extreme. Why? Nothing comes before here. So yes. In the drawing you see it. Yeah, I get the concept because if you look at it, they are literally similar, right? Because this is this. I'll show you why. I'll show you why. Just keep it pending. I'll show you why. When we come to join the diagram there, if you don't put condition, you'll not get the answer. But just keep the question pending. I'll show you why. So he's asking, why do we have to? Because if you look at the process, we are literally going over it over and over again. Like, look at this now. This answer was the answer to the first one. Check. And we're having this. Then look at condition 2. We have this answer. Condition 2 here is the same answer as condition 1 here. So why exactly am I repeating it? Condition 2 here, look at this value here. Okay, condition 2 here, look at this value here, is the same thing as condition 1 here. So why exactly am I repeating it? I will show you in the calculation. Just keep it pending. When it comes to draw the diagram, you now see it there. If I don't put this, you won't get the correct diagram. You would not. We'll just keep it pending. We'll come to it. All right, keep it pending. I'm done with shear force calculation. The second calculation is now what there? Bending moment calculation. All of these things are for one question. And what you're having here, we've not even drawn diagram. These are pre-diagram calculations. And this, they won't even say this kind of, is this still easy for you? Check your past question and you see. All right. So you get your value of reactions, RA, RB. When you're done, you now do shear force calculation. When you're done, you now do bending moment calculation. When you're done, you now do again there, the name diagram. Welcome to the hood, right? Let's now do bending moment diagram. Bending moment diagram. This is literally the cheapest example you can find. Cheapest. We'll do the real deal later. So please listen. Listen. For your bending moment calculation, you are literally following the same distance interval as your shear force. You are following the same distance interval as your shear force. The intervals we use was as x equal to 0, at x equal to 2, at x equal to 5, at x equal to 7. We are going to still use the same thing. So at x equal to what? 0. What do we have? We have that the bending moment, two conditions only works for shear force. Two conditions does not work for bending moment. Having said that, now look up. Look up, please. Look up. Look up. Look up. At x equal to 0. Now listen. When we say at x equal to 0, what that simply means is that I'm taking the moment of the forces to 0. Now, let me give you a better perspective. When we did at x, listen, when we did at x equal to, if you observe how we handled shear force, at x equal to 0, we got RA. When we said at x equal to 2, observe that we're considering only the forces on the left-hand side, which was just this. When we did at x equal to 5, we're considering only the forces on the left-hand side. So it literally, until the force passes you, consider this side. That's the concept. Let's use the same concept for bending moment. At x equal to 0, what force do we have here? RA. We have RA there. Please, at this point, what's the distance of RA? 0. Why? RA is what there? At that point. So it gives you what there? 0. RA times 0 gives you what there? Note, bending moment must always start with a 0. Shear force must always end with a 0. Shear force might start with a 0 or might not start with a 0, but shear force must end with a 0. Meanwhile, bending moment must start with a 0. Why? We'll always take at x equal to 0. And if the distance is 0, moment is force times distance. So irrespective of the magnitude of the force, it becomes what there? That thing times what there? 0, which gives you what there? 0. So bending moment must always start with what there? 0. With time, I will skip this. I will say at x equal to 0, bending moment equal to what there? 0. You should know why. Following the shear force condition, after at x equal to 0, my next one was at x equal to what there? 2 meters. In essence, I will follow the same intervals. If you took at x equal to 0, 1, 2, 3, 4, 5, 6, 7, bending moment, you will still take at x equal to what there? 0, 1, 2, 3, just follow the same interval. At x equal to 2 meters, the bending moment is equal to, so look up, look up, look up. Please understand this, At x equal to 2, this is 2 meters. Please, before this point, what are the forces you have there? Just RA, Abi. So because what the moment is force times distance. This RA, is it giving you clockwise or anti-clockwise? So because what there? RA times the distance is what there? 2 meters. So listen. At x equal to 2 meters here. At this point, what about the 20? Do I add it? You don't have to. Again, this one is not two conditions. Two conditions only work for shear force, not bending moment. So for bending moment, just go straight to taking the moment. So for this one here, the two forces at play would be this and this. But if you observe something, when we do moment, we don't include the force at that point then. We don't. Because if I'm at x equal to 2 here, at this one here, I have two forces actually, which are this and this. But the only one that will have a value is what there? This one, because it becomes this times distance. This one here is now 20. If I take out 20, what's the distance of 20 here? Huh? For 20, what will be the distance? 0. Why? 20 is what there? At that point. So it becomes what there? 0. So in essence, I will just take for only one there, this one. And that's equal to RA is 22.86 times 2. That's equal to 12, 16, 18, 2, 8 point, 12, 5, 4, 45.82. 7, 2, 8, 6. Okay, 16 plus 1, 17. 25.72. By the way, moment is force times distance. The force here is in 1 unit. The force, kilonewton. The distance is 1 unit. Combine it becomes what there? No, not per. Force times distance, not force by distance. Kilonewton meter. Force, kilonewton times distance, meters. Kilonewton meters. Multiply them. You're not dividing them, so it's not per meter. It's meters. The next one will be at x equal to 5 meters. This is what someone now do. Let's do one Saturday class and revise everything before exam. This thing. One Saturday class. At x equal to 5 meters, what's bending moment? Bending moment is equal to, look up please, at 5 meters, here's where we are. Here. Please, before this point, how many forces do you have? 2. So please, what's the first one there? RA is going this way, clockwise or anti-clockwise? So it becomes RA. For RA, what's your distance? Hey, check. What's the distance from RA? 2 plus 3, that's 5. Again, I have a second force, 20. 20 is coming what there? Anti-clockwise. Trace it, it's anti-clockwise. So it becomes what there? Negative. Minus 20. What's the distance of 20? 3. I would omit the force at that point. Abby, we know why. So we are not start stressing why we omit the one at that point. Why? Because this one becomes what there? This times what there? 0 is at that point. So you omit it. What we did at x equal to 2, we use only RA. Look at it. So when you're doing bending moment, you're only taking the force before that point. That's just all. Right? This one here. Before this point, I had RA. So it was RA times 2. Come to 5. You use the 2 before that point. Right? Clockwise times 5. Anti-clockwise minus 20 times 3. That's all. You don't include the one there. So this is equal to RA is 22.86. 22.86 times 5 minus 20 times 3. Give me final answer, please. Sorry? 54 points. Give me in 2 DP now. 3. We just 3 on the dot. Okay, 3 kilonewton what there? Meter. Not kilonewton, please. Kilonewton meters. Our last point at x equal to 7 meters. At 7 meters, what is bending moment? Bending moment at 7 meters, that's here. Now let's go. So at this point, don't forget, I'll take only the forces before that point. I will not include the force at that point. So let's go. This man here is what there? Clockwise, coming like this, that's clockwise. It becomes RA times the total distance, 2 plus 3 plus 2, that's 7. So RA times 7, RA times 7. That man is checked. Next up, this man is coming down this way like this. This is what there? Anti-clockwise. It becomes what there? Negative. Negative of the force is 20. Distance from here to here is what there? 5. Negative 20 times 5. Negative 20 times 5. Okay? Before here, I still have one more. That's 30. 30 is coming down this way. Down this way becomes what there? Anti-clockwise. Look at this. Anti-clockwise becomes what there? Negative. Negative times, what's the force? 30. What's the distance? 2. Minus 30 times 2. That becomes minus 30 times 2. This is equal to RA in value is about 22.86 times 7 minus, this gives you 100 minus 60. Hold on, what do you have here? 160.20.02 minus, what do you have here? 160. What do you have here? 0.02. This should actually give you what there? 0. Bending moment must end with a 0. I know I mentioned this concept. Where to give you 0.0 something. And I said the reason why you have this word there, approximation. My RA, I was using what there? Approximation. So assuming RA gave me 22, a whole number, and RB gave me, let's say, 25, a whole number, this will give you a perfect 0. So the reason why you're having 0.02 is because I've been working with what there? Approximation. But remember that what there? Bending moment would always what there? End in what? 0. Here's your gist. Shear force might or might not start with 0, but shear force must end with 0. Bending moment must start with 0, and what again there? Must end with 0. All right. At this point, we can now draw shear force. So we've not even started drawing the shear force. Though. Let's now draw shear force. All right, let's now draw the shear force and bending moment diagram. I put something in the WhatsApp group this morning. I think so. When I said you could come with a graph sheet, because depending on your lecturer, some lecturers will say you should sketch it. If they say you should sketch it, that means you're supposed to draw it in your answer sheet or on the answer sheet, right? With your pen. Some will say use graph and do it. So you have to plot it on a graph. Whichever way, see how it works. When it comes to drawing your shear force and bending moment diagram, your first task is to redraw your beam. Your first task is to redraw your beam. I have this one here. This was the RA point. I would say RA, the value was equal to, give me RA, 20 what? 20.86 kilonewton. This was RA. Somewhere along the line, let me just use here. What's the value there? 20, 20 kilonewton. Okay, somewhere else along the line. Um, mm, That was what? 30 kilonewton. And we had ROB here. ROB, whose value was what? 27.14. 27.14 kilonewton. So listen. At every point where you took intervals, you draw straight dashes downwards, right? Just short, thin dashes downward. So carry your meter rule, place it here, draw dashes downward. Some will say use straight line. Well, anyone, whether straight line or dashes, anyone. From here, listen, we took intervals at x equal to 0, at x equal to 2 meters. 2 meters, take dashes downward. I'm having 1, 2, this. Okay. At x equal to 5 meters here, I'll still take dashes downward. Okay. At x equal to 7 meters, that's this point. I take dashes downward. All right, so we have this. So basically, I'll be drawing these lines downward, straight at the point where I took intervals, right? I took intervals at 0, 2, 5, 7. So I'll draw dashes straight. You draw two diagrams on this stuff. Draw your shear force above at the top and bending moment below at the bottom. Now, those of you that was asking why we didn't two conditions, I'll answer you here. Now, so look up. First things first, so you choose one place there at the top. All right. Please check, please. Please look up so you get this, please. Look up. At x equal to 0, please check. What's the value of the shear force? 22.86. So I'll come here upwards. Please watch this and get this. Please watch this first. You will draw. I'll give you time to draw. Just watch this. I'll call this point here. Let me call this point 22.86. That's at this point. All right. Now check. At s equal to 2, you had two conditions. Condition 1, what's the value? So we'll take here, this same here. Condition 1 is here. That is 22.86. That's condition 1, kilonewton. What's condition 2? Now, 2.86, will it be above this or below it? Hey, 2 point this. You're drawing graphs. If from here to here is 22.86, where do you think we find 2? Is it above this or below? Below. Now, this is that 2. This is 0. 0, 1, 2, 3, 4, up to 22. So 2 should be somewhere close to what there? Abby? Yes. Somewhere close to this. So let's assume here. We'll assume here. We'll call this what there? 2.86 kilonewton. Keep this pending. Come to at x equal to 5 meters. You had two conditions. Condition 1, what was the value? It will be the same place as here. So here like this. That's this as 2.86 kilonewton. What's condition 2? Minus what? Minus 27.14. Will it be above or below? It will come down, Abby, to negative. So I'll come here down. I'll call this. Give me the value. Minus what? 14 kilonewton. All right, that's this point here. Come to at s equal to 7. You had two conditions. What's condition 1? Sorry? This is minus 27. Okay, let me just draw it. Okay, that was 27.14 kilonewton. What's condition 2? 0. That's this point here. Now, see the movement. See the movement. You're going to trace it from the beginning, follow the boxes till you get to the end. I started from here, so from here to this point. At every junction, put an arrowhead. That's the first one here. At condition, at x equal to 2, I had two conditions here and here. You will trace this here first. It becomes a straight line like this to this point first. At every junction, put an arrowhead. Then it comes down to this point here, condition 2, comes down this way, an arrowhead, stop here. Trace to the next one here, this one here. This man goes this way up to this point here. At every junction, put an arrowhead. From here, it's coming down to this point here. Here, I'm coming down to this point. From this point to the next one here, it goes this way. You have this. From here, it goes up to 0. So I'm having 0. At every junction, put an arrowhead. Every part above the datum should be called a positive. I will come here, I'll call it positive. Why? It's above the datum or the horizontal line. This part is above horizontal line, it becomes positive. This part is below the line, so it becomes what there? Negative. I have this. Finally, shade it. I'll shade this like this. Now shade this like this. All right, guys, so you successfully drawn the shear force diagram. And now write this as FS or SF, shear force. SF diagram. Let's now draw bending moment diagram. We're not done, no? Let's draw bending moment, please. For bending moment, again, now listen, listen and take note, listen. In my shear force, I had negative values. I came down here. Please check. In bending moment, do you have negative values? Check. Look at x equals 0, 2, 5, 7. Any negative? What that tells you, so look up. Since there are no negative values, what you do is that I will take the datum at the very word there, bottom. Why? I am not expecting a negative value. Listen and listen good. The next one we'll do, we might have a negative value. So if I'm drawing bending moment and I have negative values, I'll have to take this my word there up. Why? Positive my word there, negative. But there's no negative, so just keep it at the extreme. Everything will be positive, so it'll be up there. At x equal to 0, it was what there? 0, Abi? Check. At x equal to 0, bending moment was 0. At x equal to 2, what's the value? Sorry? 45. At x equal to 5, what's the value? Okay, no problem. Now, this is why I'm asking, because you're drawing this thing with sense. You're drawing 45 and 54. So common sense will tell you that don't go and carry this man and put 45 here. If you put 45 now, where will 54 be? Now here? No, now. So use common sense. So there's a higher one, 54. So I'll draw this one up, but it should be small. So I'll have 45 here and what there? 54 here, and then 0. Before you go and draw 45, you drop it here. Now to get 54, hey, where 54? Now start squeezing. No. Use your, look ahead. All right? Let me keep it here. Okay? So I'm just come here and say this is 45 on what? 72 units, kilonewton meter. That's here. Now this is sketch. If they say you should use graph sheet, it means you should calibrate it very well. Right? So you can take this in what there? In twos. Right? 2, 4, 6, 8, 10. When you get to 22, you'll find the points there. Next one is what there? 50 what? This one is 54.3 kilonewton meter. And then what there? 0. So sketch it become from here. Use straight line. Draw straight line away. Draw straight line here. Okay, like this. Okay. Draw straight line this way. This is above that thing, so it becomes what there? Positive, right? Always above that and positive, then shade it. Please draw straight lines. So this is just a board sketch. So with this, you know what is called your BM diagram. This is now the bending moment diagram. After this, we are not still done. We still have to do two calculations. Number one, the position of the bending moment diagram. Number two, the point of contraflexion. After these two things, listen, after shear force and bending moment diagrams, you ask to find something called the critical points. Critical points. There are two critical points. Number one is the position of maximum bending moment. Number two is the point of contraflexion. Hang on, we'll deal with this in our next example. But listen up, look up, look up. When we say position of maximum bending moment, listen. Lastly, they asked to find this thing, the value and the position. Listen, note this. When it comes to finding position, you ask to find the maximum bending moment and the position of the maximum bending moment. This is the condition. The condition is that the maximum bending moment will occur at the point where the shear force diagram cuts the x-axis. Please listen. Your maximum bending moment will occur at the point or at the position where the shear force diagram cuts the x-axis. If I look at this diagram here, this man is going like this, like this, like this, like this. This diagram only cuts the x-axis at where there? At this point. You can see it here. In essence, this will be what there? The position of the maximum bending moment. In essence, the maximum bending moment occurs at this point. Why this point? This is the point where the shear force diagram cuts the x-axis or the horizontal line. In essence, the maximum bending moment occurs at, from here to here is 5 meters, at 5 meters. What's the value here? The value is what there? 54.3 kilonewton. So we say the maximum bending moment is 54.3 kilonewton meters and occurs at what point? At this point. How do you describe this point? This point is 3 plus 2. That is 5 meters from which end? From this end. This end was labeled A. From A. You can say, and occurs at 5 meters from A. That's it. So this is the first condition. It's called the position of maximum bending moment. The second condition is called the point of contraflexion. In position of maximum bending moment is where the shear force cuts the x-axis. The point of contraflexion occurs where the bending moment diagram cuts the x-axis. For this case here, observe that bending moment did not cut x-axis. It was all above, it didn't cut this. So in this question here, there is what there? No point of contraflexion.